It's by Dr. Takeuchi. Tomography with array analysis of triplicated field levels.
Good afternoon. My name is Nozomu Takeuchi, and I'm from ERI University of Tokyo. And in this study, we conducted the array analysis of the triplicated P waveform data and obtained a tomography model with several important features. And the data used in this study was obtained by the international collaboration project among China, US, and Japan. And as has been pointed out by a previous speaker, one of the most significant difficulties in seismic tomography is the existence of the mantle discontinuities. And due to the discontinuities, travel time curves get very complex, and multiple phases arrives at a single station. And if we want to accurately constrain the structures in the vicinity of the discontinuity, we have to utilize the information of the secondary phase as well as the initial phase. And fortunately, we have deployed 120 broadband sensors, and they have an ideal geometry to reveal the detailed structures in the subduction region. And in this study, we first conducted the array analysis and measured the travel times of both initial and secondary phases. And using the measured travel times, we conducted the delay time tomography for the P-velocity model. And the obtained model has significant discrepancies compared with the previous model, especially in the vicinity of the discontinuities and new implications for the subduction processes obtained. The method in this study has two notable features comparing with the conventional method. And first, we use both the initial and the secondary phases, and the second is rigorous phase associations. I mean, we rigorously associate these are travel times for the upper mantle phase, and these are for transition zone phase, and these are lower mantle phase. In contrast, in the conventional method, phase associations has large uncertainties. And the former should improve the resolution, and latter should improve the accuracy of the obtained models, and the existence of the array data is critical for these improvements. And travel time measurements are based on the waveform fitting or waveform inversion. And we first describe the synthetic seismograms using several parameters such as amplitude and arrival times of each phase. And we determine the optimal parameters to minimize the misfit between the observed and synthetic seismograms, so we can obtain the arrival times of both initial and secondary phases, even if two phases are overlapping with each other. And we measured almost all available P data for necessary, but to improve the coverage, we add a few data, FNet data, the network in Japan. And total number of the travel times used are about 40,000. But for the discussions in this talk, the data within the triplication distance is important, and about half of them are triplicated waveform data. And this shows the coverage of the replication data, and white circles denote the bottoming points of each ray path. And our model has a good resolution beneath Japan Sea and Japanese islands between about 200 and 800 kilometer depths. And this is a model obtained by this study. And comparing with the previous model, we have several significant discrepancies. Note that the data set used in these two studies are completely independent, and the previous model analyzed the ISC catalog data. And the overall features are consistent with each other. But the most striking discrepancies should be the low velocity anomalies. 8 of the 410 are observed only in our model, and they are very unclear in the previous model. And looking at the structures in the transition zone, we can confirm the high velocity anomalies associated with stagnant slabs. But in our model, we can clearly confirm a hole in the stagnant slab. And the location is precisely beneath the Bekto or Chambai volcano, and suggesting the origin of this anomalous volcano. And as for the high velocity anomalies, 8 of the 660, the horizontal extent is smaller in our model comparing with the previous model, and suggesting the morphology of the stagnant slab is more complex than we have thought before. Now, I will show the details of the focus features. First, as for the low velocity anomalies, 8 of the 410, it has good spatial correlation with the location of the stagnant slabs. And this shows the radial correlations, and we can see the structures 8 of the 410 and structures in the transition zone are nicely anticorrelated. And this is a comparison of heterogeneity patterns, and we can see low velocity anomalies are located above the high velocity anomalies, 8 of 660, and these correlations suggest that these anomalies some relation to the subduction processes. And this is a typical vertical cross section in this region, and we have a stagnant slab, and we have low velocity anomalies above it. But beneath the Bekto of Chambai volcano, stagnant slabs are unclear compared with the adjacent sections. And we also see the low velocity conduit arising from the 410 and reaching to the surface. And the existence of this kind of low velocity conduit has been pointed out by previous regional tomography by Lei and Chow, and they have also pointed out some low velocity anomalies arising from the 410 discontinuity. And observed features may be interpreted in terms of water transportation. And beneath Japanese island, using the dense network, very detailed structures are extensively discussed. But unfortunately, because our islands are so small and narrow, so this is only cross-section where we can trace the subducting slab into the transition zone. And this is why the data in China and Korea is very important for this problem. And here I'm showing the results of the receiver function analysis by Kawakatsu and Yoshioka. And red denote the positive discontinuity, and blue denote the negative discontinuities. And we can confirm the top surface of the subducting slab down to about 350 kilometers, and it is probably corresponding to the bottom of the hydrous layer dragged by a subducting slab. However, this surface cannot be confirmed in the transition zone, and instead this discontinuity appeared to have seamless continuation to the faulting discontinuity corresponding to this red curve in this cartoon. This result may be suggesting the hydrous layer is merging to the partial melt layer 8 of 410. And due to this water transportation, we may have low velocity anomalies 8 of the 410 in this region. And as for the structures beneath the volcano, because stagnant slab is not clear in this region, something may be arising from the lower mantle, and this should be alternative of the BMW model. And actually, the tomography model by Wang and Chow detected the low velocity anomalies in the lower mantle and less clear high velocity anomaly in the transition zone compared with adjacent regions, and we have low velocity anomalies in this region. So if they chose a different color palette, a similar implication may be obtained. And finally, I want to discuss the morphology of the stagnant slabs, and the details are discussed in this Japanese island, and together with the 660 topography. And results suggest that we have very large depression of 660 with an amount of 40 kilometers. But the horizontal extent of large depression is smaller compared with the horizontal extent of the high velocity anomalies, and the deepest, largest depression is located in the vicinity of the point where subducting slab first touched the 660 discontinuity. And in this study, we try to confirm whether these features are common features in our studied region. However, it is not an easy problem, and mapping the topography of the discontinuity beneath the oceanic region is especially difficult. For this reason, we used a slightly different approach from the previous studies, and we analyzed what we call SCS reverberation data and tried to map the topography of the discontinuity. And this approach requires very high quality data, and for this reason, the most of data used in this analysis were FNet data. So only in this region, our model has good accuracy. And horizontal extent of the high velocity anomalies are very wide in the mid-transition zone, and it is very pronounced in the conventional. It is more pronounced in the conventional model, but obtained topography shows very localized depression. The region with blue, region in blue denote the region with depression, and the red region denote the region with 660 elevation. And we also see the what we call the subslab region is not normal, but we have some elevation of the 660. So we can see this is also anomalous region. And comparing with the obtained tomography model 8 of 660, the regions with depression appears to locate on the peril of the high velocity anomalies 8 of 660. And looking at the vertical cross sections, we can confirm that the region with largest depression is located in the vicinity of the point where the subducting slab first touched the 660, and it appears to be a common features in a studied region. So in conclusion, we have detected low velocity anomalies 8 of the 410, and they have good spatial correlation to the stagnant slab, and probably they related to some subduction processes, and we detected the hole in the stagnant slab and the low velocity conduit beneath the volcano, and we detected the localized depression of 660 in the vicinity of the point where subduction slab hit to the 660. That's all. Thank you very much.
Thank you. Any comments, questions? I have a question, Takeuchi-san. You use a lot of regional earthquakes.
Yeah.
How about the accuracy of those hypothetical parameters?
Okay. Yeah. In this tomography, we iterate the inversion for the source parameters.
Can you show the location of the earthquake?
Okay. I'm just in this inversion, we just modify the origin time, and we do not modify the hypocenter. It is due to
the hyperlocation could be quite
yeah, but unfortunately, the data is only the local network, so it is not. It is impossible to locate.
Will certainly affect your result.
Yeah, but because if we modify the origin time, we can largely remove that effect. And actually, we compare the model with and without source parameters modification, and overall pattern is not changed at all.
Okay.
Yeah.
And another point is your proposal is a slab hole, slab window.
Yeah.
Right in East Shanghai.
Yeah.
How are you certain about that?
Yeah, I'm quite certain. Yeah. Yeah. First of all, different tomographic images also show the hole in this region, and
but that's a top of the mantle transition zone, not the slab itself.
So,
that's above the slab. Okay.
Okay. Yeah.
That's above the stagnant slab. Not in the slab. Not in the stagnant slab.
Hole is
right. This hole.
This hole is in the
right. It should be around here.
I
not here.
Yeah. Okay. Yeah. For the 660, it's not the high velocity anomaly is absent in Venezuela's volcano. So we have absence of the stagnant slab in this region.
Dr. Lee, how about you? You think you can?
Yeah, if you think the thickness of the slab is around 140, and this hole might be located just above the slab.
Not in the slab.
Yeah, not in the slab. Around the boundary, I think. This is the first thing, and the second thing is that in your SCS study, what's the value you inverted for? It's the velocity of the velocity and multiple the rho. I do know that revenue has using the SCS multiples to get the lower velocity zone beneath the volcano. And what's your?
My result. Okay. Yeah, the Lebanon signal is not very clear in my analysis, but yeah, in some source station pairs we can confirm such signals, and yeah, maybe the low velocity anomalies in this region, 8 of 410, is not universal ubiquitous features in this region, but it's localized feature, and for the first question, yeah, this section is everything. We can confirm only the subducting slab, and we don't have any stagnant slab, and the hole is not in the slab.
Okay, I think it's a very interesting point, Takeuchi-san.
Yeah.
And suppose you have a hole, did you conduct some synthetic tests?
Yeah. Okay.
For example, you have a hole, see if you can reconstruct it or not.
Yeah. Okay. We can.
And another aspect that Dr. Lee, if there's a hole, if your uniform modeling can distinguish it.
Yeah, I think if you do the Triplicated modeling, you should have something.
Okay. Yeah, try please. Another points, another questions. Okay.
So, how does this compare with the models that Darpeng Zhao showed earlier?
Yes. Okay. This. Wait. This one. This one. Yeah. Yeah. Okay. This is Darpeng Zhao's model. Yeah, and if you change the color palette.
So you like the BMW, but you need the whole.
Yeah, I like whole.
That's only difference, I think.
Yeah, but my point is, if you change the color palette, we should be able to obtain the similar picture, I think.
Well, you have to confirm that you have enough repass coverage and crossing.
Yeah, the teleseismic data and teleseismic data from Indonesia and Papua New Guinea and Fiji Tonga covers all of these regions, and we have very nice coverage in this region.
Okay.
No problem.
Okay. Yes.
See also when you show the different slices.
When you show the different slices, the low velocity anomaly below the slab is less pronounced in your tomography compared to the one of
Below the slab.
below the slab.
This one. This.
Yeah.
Okay. Okay. And path coverage is in because we analyze the secondary phase, so the resolution in the vicinity of the discontinuity should be.
So you showed our first tomography, then 2005. But you showed 2009 paper. I just showed.
Okay, yeah.
That's much better.
This is a past.
Yes, this is our first line. So we have a low resolution in the Mantle transient.
Yeah.
But you can see my talk. We have a new model. It's beautiful.
I confirmed. Your high velocity model is not so strong compared with adjacent position.
Okay. Anyway, our new model don't have a hole there, but it's very interesting topic.
Yeah, no. If you change the
I hope
color
that you can also Dr. Lee, you can further advance your study and we can discuss such a topic in the future. Okay. I think we have to close this session. Okay. And we have 5 minutes. Let me see. How many minutes? Can I have 5 minutes break?
Yes.
And let's start at 3:45. Okay, for next session. Okay, thank you very much.